Hi. So in this one, I'm going to look at what we're going to call the general gas equation. And there's no experiment for this. What we're going to do is we're going to combine all three of our gas equations, or our gas laws. So we have Boyle's law, we have Gay-Lussac's law, and we have Charles's law. But in each one of them, they're keeping one thing constant. So with Boyle's law, for example, we kept temperature constant. But there'll be often situations where none of them stay constant. That if you heat something up, if you heat a container up, it's going to do two things. It's going to expand, and also the pressure is going to increase. And so really the three gas laws that we've looked at so far, they're dealing with special cases of where one of them stays constant. But in general, what we'd find is that the general gas equation would apply. Now, there's no formula for this. Sorry, there's no experiment for this, and all we do, and this will be very quick because all I'm going to show you is the course notes and then the formula that we have for it. So from there we have on page 22. We have just a recap of the three gas laws that we have so far, namely that pressure is directly proportional to the inverse of volume, pressure is directly proportional to temperature, and volume is directly proportional to temperature. Putting all three of these together, what we'll have is that pressure being directly proportional to temperature and volume. But when we work out through there, we'll have pressure times volume divided by temperature, as long as that's in Kelvin, remember, is equal to a constant. And then, as before, we can look at a before and after scenario. So pressure times volume divided by temperature at the start is going to equal these terms after. Okay, so we'll do a worked example, and then that will be us done. Okay, so we're going to have a balloon. It has a volume of 1.5 litres with a pressure of 110 kilopascals at temperature of 20 degrees C. And if we have calculate the new volume, so we'll say V2 is equal to this. If the pressure has increased to let's say 180 kilopascals, and we're going to have a temperature of 60 degrees. Okay, so in all these cases you're only ever going to have one unknown, and it will always be one unknown, and it will just depend on which one it is that you have to rearrange your formula for. But the rearrangement is exactly the same as before. So if we get a table, just first of all, we'll have P1, V1, T1, and we'll have P2, V2, and T2. So the three on each side. V2 is what we're looking for, pressure, so 180 kilopascals, 110 kilopascals. We'll have volume 1.5 litres, temperature 20 degrees C, and so that's going to be 293 Kelvin, and then 60 degrees C, 333 Kelvin, and our formula. So formula P1 V1 over T1 is equal to P2 V2 over T2. Make our substitution if you wish, but we, as before, are going to rearrange first. So we're looking for V2, and it's just as before, we're cross multiplying, so V2 must be on its own and on the top. So we're going to cross T2 up to there, and we're going to bring P2 down to there. And so V2, and this starts becoming a bit of a mouthful, that will have P1, V1, T2, and that's going to be over T1 times P2. Then we just substitute our numbers in and solve from there. I'm going to leave it as kilopascals. I'm quite happy. The units, because the pressures are going to be over each other, then the kilo bit of the pascal is just going to disappear anyway. So 110 is fine, times 1.5 times T2, which is 333, over 180 times 293. And that's going to give me 1.041, so let's see, 1.04 litres. Yep, so I'm just double checking my working. So yeah, so 1.04 litres. So despite what my diagram is saying, it's not getting bigger at all, it's going to get smaller in volume. Which is okay, because what's happening is where the increase in pressure is greater than the relative increase in temperature. This is the percentage increase of pressure there is greater than the percentage increase of temperature, and so we're having a reduction in volume to meet that, and that's fine. It won't necessarily be obvious what's going to happen with what, because you have the 6 variables in there, and I should probably plan what I'm going to actually write down before starting to record these, but I don't. I just usually go. Usually when I'm in class, I shout at you guys to give me numbers, and they sometimes work and they sometimes don't, and so I'm just carrying on that and making up numbers as I go along. But the maths is all correct. The way to work out the equations is all correct. Just for completeness, I will do. I'm not going to do another worked example because we've got plenty of them. The course notes are full of them, and then there'll be the problem books which we'll use as well. So you will be thoroughly well trained in the use of these formulas by the end of this little bit of course. But if we wanted to rearrange, say, for T1, and so remember it needs to be on its own and on the top. So we're going to bring T1, and we bring T1 up there. So T1 is now on its own, but filled with other stuff, and so P2 V2 goes down. P1 V1, that stayed where it was. T1 moved up, P2 V2 goes down. And don't forget about T2. T2 has got to go away as well, so that goes up to the top. T2. And so that would be a rearrangement there. So T1 is equal to P1 V1 T2 over P2 V2. Okay, well, thanks for watching, and I'll see you very soon with the last lesson in indeed properties of matter, which would be a general overview of kinetic theory of the gas laws.